So in general, I have three types of trig substitution I can do. If I see an a minus x squared, a squared minus x squared, I'm going to do the substitution x equal to a sine theta. If I see an a squared plus x squared, I'll use the substitution x equal to a tangent theta. And if I see x squared minus a squared, I'll use a secant theta. And these are all corresponding to these three triangles given here. And we just label them slightly differently, and then we have the Pythagorean theorem that gives us the third side. In general, this is kind of my summary. Like I said, if you see a squared minus x squared, then we're going to let x be equal to a sine theta. And when we substitute this back into the problem, we're going to get a squared cosine squared theta. If we see a squared plus x squared, we'll use x equal to a tangent theta. And when we substitute this back into the problem, we get a squared secant squared theta. Finally, x squared minus a squared should be x equal to a secant theta. And when you substitute this back in, you get a tangent squared theta. So for example, let's find the arc length of the parabola y equal to x squared between negative 3 and 3. So we've done arc length before. We start by finding the derivative, which is 2x. We then square it, which gives us 4x squared. So I'm looking at the integral between negative 3 and 3 of the square root of 1 plus 4x squared dx. So, for this one, this is going to be of the form for tangent. So, normally I would let x be equal to a tangent theta. However, that gets a little more complicated with this 4 in front here. So instead I'm going to let 2x be equal to a, which is 1, tangent theta. Which implies x is 1/2 tangent theta. This also means dx is 1/2 secant squared theta d theta. So this is the integral of, we have the square root of 1 plus 4x squared, and like I said in the last slide, when I do this substitution of tangent back into the problem, I get a squared secant squared theta. That's a little more complicated with this 1/2, but in general, not really. We get 1/4 secant squared theta times dx, which is 1/2 secant squared theta d theta. Simplifying this then gives me 1/4 secant cubed theta d theta. Using the reduction formulas, this is going to simplify to 1/2 secant tangent plus 1/2 times the integral of secant, which is ln secant x plus tangent x. So this is 1/8 secant x, or sorry, these are all thetas, secant theta tangent theta plus ln of the absolute value of secant theta tangent theta. So you'll notice I didn't change my bounds because it can be a little bit trickier to find these inverse tangents. However, we are going to go ahead and substitute back into x. So I have my triangle. Here's theta. For a tangent substitution, this is x. This is a. And this side is the square root of a squared plus x squared. So I have 1 over 8 times secant of theta. So secant is 1 over cosine. So we have the hypotenuse over adjacent. So square root of a squared plus x squared over a times tangent of theta. Sorry, I've been messing up my a's here. This is 1 over 4. And this a as well will be 1 over 4. Tangent of theta is x, or rather 2x, plus ln of the absolute value of secant theta, which we just said was the square root of 1/2 squared plus x squared over 1/2, and then tangent theta, which is 2x. All between -3 and 3. So you can see that this actually does get fairly complicated. Let's try this one. So this one doesn't look like either form, so we're going to have to complete the square first. So we'll start with that first. I look at the number in front of x, which is 6, divided by 2 is 3, and squared is 9. So I'm going to both add and subtract 9. Rearranging this gives x squared plus 6x plus 9 minus 4. So x plus 3 squared minus 4. This is the integral of the square root of x plus 3 squared minus 4 dx. So I'm going to let u be equal to x plus 3 and du equal to dx. So this is the integral of the square root of u squared minus 4 du. And now I'm going to do my substitution for trig. This is of the form u squared minus a squared, so this is a secant substitution. I'm going to let u be equal to 2 secant theta, which means du is equal to 2 secant theta tangent theta d theta. So now I have the integral of, my identities tell me when I stick in u equal to a secant theta, I get a squared tangent squared. So this is 4 tangent squared theta times du, which is 2 secant theta tangent theta d theta. Rearranging this, I get 4 secant theta tangent squared theta d theta, which I'm going to rewrite in terms of secant. So rewriting tangent squared in terms of secant squared would give me secant squared minus 1. So I have secant cubed theta minus secant theta d theta. I'm going to have to use the reduction formula here. And for secant cubed, I get secant theta tangent theta plus, 1/2 of all of this, plus 1/2 the integral of secant theta, which is ln secant theta plus tangent theta. And then I have minus the integral of secant theta. So minus ln of secant theta plus tangent theta. If I think of my triangle here, here's theta. This side here will be x squared minus a squared. Here's x, and here's a. So multiplying this out, I have 2 secant theta which is u. And this is minus 1/2 times 4, so minus 2, times ln of secant theta, which is 1/2 u, plus tangent theta. So tangent is going to be my opposite over adjacent. So x squared minus 4 over 2. Sorry, in this case we're still with u's. So u squared minus 4. And then we need to switch back to x's. So I actually have x plus 3 minus 2 ln of 1/2 times x plus 3 plus the square root of x plus 3 squared plus 4.